In this video, we're going to see kind of for the first time how chemists can think about a situation where you have a poor leaving group and make it into something better. And one of those leaving groups that we're going to focus on is the OH group as a leaving group. And we're going to see how we can either convert it to OH2 plus, or we can convert it to a sulfonate, or we could convert it to one of the halides. So in essence, we're taking a functional group and we're going to be making it into a good leaving group. Now, why would we want to do something like this? Well, because the essence is we want to create a better leaving group. And if you take a look at all of the substituted alkanes, alcohols are cheap and they're widely available. And therefore, they become very good starting material. But we saw in that table that alcohols have an ROH group. So the OH group is the problem, right? And because that OH group is a poor leaving group. But if we could make it into one of the better leaving groups, then we could do substitution reactions on it. And it happens that there are many ways to circumvent this problem. So we can protonate, which essentially takes that OH group and makes it into the OH2, water, as a leaving group. Water is a good leaving group, right? On that table, water was a good leaving group. We can also convert alcohols to sulfonates, and we'll see how we can do that. And lastly, and probably the most widely used method of circumventing the problem is to convert to halides. And so we're going to explore in this video how to do each one of those. And we're going to look at protonation first. So one of the ways that we can make alcohols into a good leaving group is by reacting them with acids. So if I take an alcohol and I react it with HBr, strong acid, I know that a reaction is going to ensue in which I get a proton transfer. Right? This is very similar to an alkene reacting with HBr. So non-bonding pair of electrons on the oxygen, that's the HOMO, is going to react with the sigma star LUMO of the HBr bond, breaking that hydrogen-bromine bond, and we get essentially proton transfer plus bromides coming off. Well, we get OH2, which is a good leaving group. So we've gone from OH, which is a poor leaving group, to OH2, which is a good leaving group. Now, interestingly enough, in this reaction, if we use HBr or HCl or HI, the halide is a good nucleophile. And what happens is that halide's going to react now with my protonated species and undergo a substitution reaction. So we get this displacement of water and we form a new alkyl carbon-bromine bond. And what have we done? We've made alkyl halides. So I can take an alcohol, react it with HX, where X is chlorine, bromine, or iodine, and I can get an alkyl halide. Alkyl chlorides, alkyl bromides, alkyl iodides in this manner, right? And in essence, I could use pretty much any alkyl halide that I really wanted to, especially primary and secondary alkyl halides. So here's an example. I take propanol, I react it with HBr, those non-bonding pair of electrons in the HOMO attack the sigma star of HBr. I get protonation plus bromide. Bromide now comes in, attacks the carbon. Now, this is the key. The bromide is attacking the carbon that has the water as a leaving group, and now that carbon-oxygen bond is breaking. Why? Because I'm essentially attacking the sigma star of that carbon-oxygen bond, displacing the leaving group, the water as a leaving group, and I form 1-bromopropane, plus water is coming off. And so you see how this what we've done there. Number one, we have just learned how to create alkyl halides out of alcohols. So that's a new reaction. Alkyl halides can be formed from alcohols with HX, HBr, HCl, HI. But also importantly is we have now transformed the OH group, which is a poor leaving group, into an alkyl halide, so an alkyl bromide, which is a better leaving group. Okay? And there are lots of reactions that do this. So here is a secondary alcohol. I can react it with HCl, and I get a substitution reaction. Here is a benzyl alcohol reacting with HBr, and I get benzyl bromide plus water, right? So this is a simple substitution reaction. Now the other thing that I can do is I can take derivatives of alcohol. So ethers, for example, we saw that ethers, the only difference between ethers and alcohols is ether has two R groups, alcohol only has one R group relative, coming off of the oxygen. But that oxygen has a pair of electrons on it, and so we can use one of those pair of non-bonding electrons and react with HBr. And you get protonation of the ether, right? So now that bromide can attack one of the carbons. Now, in this particular case, we're going to see it really doesn't matter which carbon it attacks because something else happens. So let's assume that bromide attacks the left carbon. It could certainly attack the right carbon as well. But let's assume it attacks the left carbon. And what do we get from that? Well, we get 1-bromopropane, right? But then we get ethanol coming off. And as we just saw, alcohols react with HBr. So if we have an excess amount of HBr, or HI, or HX, right, in general, typically it's HBr or HI that works the best, then we get, in essence, two alkyl halides. So the net result is, if I take an ether and react it with an excess amount of HBr or HI, then I get two alkyl bromides or two alkyl iodides, whichever, depending on the HX that I used, right? Now here's an example that's kind of interesting. If I take, this is ethyl phenyl ether, right? So I have my ether oxygen is coming off of the benzene ring. It's also coming off, it has an ethyl group attached to it, and I react it with HI. If I were to predict the products, most students would say, oh, okay, well, I'm going to get iodobenzene and ethyl iodide. In fact, I end up getting phenol and ethyl iodide. Why is that? Well, proton transfer certainly occurs, right? And so I get a proton on the oxygen. And now my iodide, my nucleophile, attacks the carbon. But for substitution to occur, this is important to understand, for substitution to occur, the carbon has to be sp3 hybridized. No sp2 carbons or sp carbons will undergo substitution. And therefore, because that the carbon on the benzene ring is sp2 hybridized, it cannot undergo substitution. And therefore, the reaction stops there. Iodide won't substitute for the OH group, and so you get phenol coming off of it. So we've seen that we could take alcohols and convert them to alkyl halides by protonating them. That's exactly what we're doing. We're protonating the OH, we're making a good leaving group, and now we're reacting it with a good, a halide to produce an alkyl halide. And we see the same trend with ethers as well. There are other conversions to alkyl halides, though, using alcohol. So alcohols can be converted to alkyl chlorides using a reagent called thionyl chloride. Thionyl chloride is SOCl2, thionyl chloride, SOCl2. Alcohols can also be converted to alkyl bromides using phosphorus tribromide, which is PBr3, phosphorus tribromide. And the reaction, so we don't, I don't care at this stage that you necessarily know the mechanism of this reaction, just that you need to understand that if you take an alcohol and you react it with thionyl chloride, SOCl2, you get an alkyl chloride. And if you take an alcohol and you react it with PBr3, sometimes you can also use PBr5, but most of the time it's PBr3. Then you get an alkyl bromide. So that's a key feature, right? Alcohols react with thionyl chloride to give you alkyl chlorides, and they react with phosphorus tribromide to give you alkyl bromides. So here's a couple of examples. In my first example, I have 1-propanol reacting with thionyl chloride and pyridine. Usually these reactions are carried out in the presence of some weak base. So pyridine is a good base to use. Sometimes triethylamine is used because one of the byproducts is HCl. So the pyridine will react with HCl and take it out of the basically out of the equation. And so you get a simple substitution reaction. So I get 1-chloropropane. Likewise, I can take something like this, a secondary alcohol, react it with PBr3 in ether. So again, ether is the solvent. Oftentimes you're going to see the reagent on the top, the solvent on the bottom. Don't let that confuse you. Reagent on the top is the important feature here. And simply recognizing PBr3 is going to substitute the OH for a bromine, right? Now, one aspect that we really haven't talked that much about is stereochemistry. And one important thing to understand is, well, what happens to the stereochemistry of a stereogenic carbon if it has an OH group? And unfortunately, with all of the reactions so far, any stereochemistry on the carbon with an OH is racemized, right? So why is that? Well, because the OH2 is a good leaving group, it's going to come off and form carbocations. And in these particular reactions with thionyl chloride and PBr3, the mechanism isn't really well understood. It's just known that you get a racemic mixture, especially with PBr3. We don't know quite what's going on. So just to clarify, what am I talking about? Well, let's say I have a reaction of a particular stereoisomer of 2-pentanol. So here I have S2-pentanol, and I react it with PBr3. What happens is I'm going to get 2-bromopentane. But the problem is I get S2-bromopentane, but I also get R2-bromopentane. And therefore, I end up with a racemic mixture. So I've started out with a particular stereoisomer, and in the process, I've lost my stereospecificity. I've lost the stereospecificity. And sometimes that's a difficult thing to get back when you have a particular stereogenic carbon. So we've seen that if we protonate the OH group, we can make a good leaving group. This is an easy way to make alkyl halides. We've also seen that we can react alcohols with thionyl chloride and PBr3 to make alkyl halides as well. But another possibility of making a better leaving group is what we call sulfonation. And this is where alcohols react with alkyl sulfonyl chlorides, to yield what are called sulfonates. So in a generic reaction, I'm going to take ethanol, and I'm going to react that ethanol with this right here. This is called a sulfonyl chloride, or an alkyl sulfonyl chloride, right? Because I have some alkyl group coming off of the sulfur. And what happens is the oxygen of the ethanol can attack the sulfur and essentially displace the chloride ion. And now the chloride ion can come in and deprotonate the oxygen, and what you end up with is something that looks like this. So now the oxygen is attached to that sulfur, right? And what we've now formed here is what's called ethyl sulfonate. Ethyl sulfonate. Now, if you look back at that table of good leaving groups, we see that that sulfonate is a good leaving group. So now we've converted the OH, a poor leaving group, into a sulfonate, which is a good leaving group. An example of this would be if I took ethanol and I reacted it with this particular sulfonyl chloride. This sulfonyl chloride is called para-toluene sulfonyl chloride. Para-toluene sulfonyl chloride, because I have the toluene that whenever a CH3 is coming off of a benzene ring, it's called toluene. So this is para-toluene. Para is substitution. If you have two substituents on a ring that are opposite one another, it's abbreviated para, or 1,4 substitution. Para-toluene sulfonyl chloride is often abbreviated, because that's a mouthful to say, as tosyl chloride, a tosyl chloride, which we abbreviate the term itself as TSCl. So oftentimes you'll see this as a reagent. You'll see an alcohol reacting with TSCl. That's tosyl chloride. And you typically use a base, again, to scavenge HCl that's being produced in this reaction, and you produce this, right? So this is what we would produce if we reacted ethanol with tosyl chloride. Now, again, oftentimes that's a lot to write. So we will take this whole thing right here, that leaving group, and we'll abbreviate it like this. We'll simply write OTS. So instead of oxygen attached to the sulfur with the two oxygens and the toluene, I'm just going to write OTS. And we call that a tosylate. So specifically with tosyl chloride, you get a tosylate. It's a sulfonate, a specific type of sulfonate called tosylate. So that group there is a tosyl group. And we use that a lot. We can use methyl sulfonate, which is called a mesylate group, or this toluene sulfonate. And tosylates are good leaving groups, and they certainly will react with nucleophiles. So I can take now my tosylate and react it with a nucleophile like sodium cyanide, where cyanide is the nucleophile, right? A lot of nucleophiles come as salts. They're anions, and they are going to have some cation like sodium, potassium, lithium, whatever, as the counter ion. So here I have sodium cyanide, recognizing that cyanide is my nucleophile, and therefore it's going to displace the tosylate, and I form a nitrile. And of course, the sodium tosylate salt comes off, right? And in a more kind of general scheme there, then I can say, well, I took an alcohol. Where did I get that tosylate? I got the tosylate from an alcohol. So I took an alcohol, I tosylated it, now I can react it with a nucleophile, and I get a nucleophilic substitution reaction. If I simply took 1-propanol in this case and tried to react it with sodium cyanide, I would get no reaction because the OH isn't a good leaving group. So you will see something that looks like this. You have an alcohol. Here I have cyclohexyl alcohol, or cyclohexanol. Again, if I tried to react cyclohexanol with a nucleophile, I would get no reaction occurring because the OH is a poor leaving group. So what do? I react it with tosyl chloride in pyridine, right? Pyridine, again, my weak base, and I get my tosylate. Now I have my tosylate. That OTS is a good leaving group, and I can react it with a nucleophile like azide. So here's potassium azide in acetone. I'm using a polar aprotic solvent, and I get azidocyclohexane. Now, the cool thing about about sulfonating alcohols. We've seen prior the stereochemistry of converting an alcohol to an alkyl chloride or an alkyl bromide. You lose stereochemistry. But when you sulfonate an alcohol, you retain stereochemistry. And the reason for this is because we're never breaking the carbon-oxygen bond. So you don't break the carbon-oxygen bond. The oxygen of the OH reacts with the sulfur of our sulfonyl chloride, but the carbon-oxygen bond never breaks. And therefore, if that carbon is a stereogenic center, there's never any stereochemistry taking place to convert the alcohol to the tosylate. So if I have a particular alcohol, here I have S2-pentanol again, and I react it with tosyl chloride, I end up with the S-tosyl pentane, S-tosyl pentane. And now if I do an SN2 type mechanism where I'm reacting it with sodium thiol here, right? So sodium thiol, I can, or sometimes this is referred to as sodium mercaptide. SH minus is mercaptide or thiolate. And if I react it in an SN2 mechanism, I know I'm going to get inversion of configuration, right? So the mercaptide is going to come in from the opposite side of the tosylate, and I get complete inversion. So now notice what happens, that the SH is from the backside because the tosylate was coming out at me. So I've inverted the stereogenic carbon, and that is my product. So I end up with a stereospecific reaction. That's called a stereospecific reaction because I've kept my stereochemistry intact. Now it's not a retention of configuration, it's a complete inversion of configuration, and I see the stereochemistry is reversed, but it's an optically pure sample. If I start with an optically pure alcohol, I can end up with an optically pure thiol in this case. And so there's some really cool features that you can do with alcohols to make them good leaving groups. And in the process, there's a lot of chemistry that's taking place here. Some that essentially eliminate stereochemistry, this particular one that retains the stereochemistry. And this is something that we're going to want to think about when we are trying to make certain compounds from certain starting materials. All right, so this hopefully gives you a good idea, number one, how we can make better leaving groups of alcohols, but number two, some of the rich chemistry of alcohols that takes place.